Hello again, and welcome to my channel. We do educational videos here, and um, try to look at theories of everything that are important, have been important to me, that I've kind of dug up and brushed off, and hopefully try to present them in a coherent way, sometimes a challenge, and we look at cosmologies and paradigm shifters, anything that I think could benefit the audience out there with their holistic worldview, their transition to 5D consciousness, and so on. And today is our 411th video on the reciprocal system of theory from Dewey B. Larson. And Larson wrote up his two fundamental postulates in 1959, and they articulated his universe of motion. And then from there, he derived his theoretical universe, about how the universe would look if his postulates were correct. And then he compared his universe to the measured universe of the legacy scientists. And he does that in the book we're focusing on today, Basic Properties of Matter in the Field of Chemistry. And so he theoretically arrives at different equations for various basic properties of matter, like the melting point. And then he compares his theoretical findings with the laboratory measured findings of the legacy science, and then compares them and explains whatever discrepancies occur, and so on. Now, Larson's two fundamental postulates are mainly we focus on the first one, and it states that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So basically, the universe is not made out of matter, not made out of energy, but is made out of motion. And motion is the relationship between space and time. Space and time are reciprocals of one another generally, and they do not exist separately, but only together in motion. And they, although you can abstract one from the other, but only by basically stopping the universe, which is really in motion. And motion is basically a fraction, with space or time as the numerator, time or space as the denominator. All of our scientific quantities are different forms of motion, including matter and energy. And motion, space, and time all only come in only discrete units. You have to have a full unit of space and a full unit of time, and before you have either one of those quantities. And if you have 1 unit of space and 1 unit of time, you have the speed of light, which Larson refers to as unit speed. And that is the background motion of the universe. So the universe is always in motion. And even if you have a universe of nothing, you still have motion. And it's a special kind of motion that Larson refers to as scalar motion. That is a motion that has a magnitude but has no specific direction, or really all directions. And you can envision this using a balloon with spots on it. If you blow up the balloon, all of the spots will be moving away from each other. So all of the spots are moving, but they're moving in every direction. Every spot is moving away from every other spot. And the only way that you can determine a direction is if you assign a reference point to one, basically saying that this one is motionless. So again, you only can really make these measurements by stopping the universe, which is against the very nature of the universe. But in order to make a measurement, you have to stop. Now he's getting into we're looking at chapter 1 of this book, Basic Properties of Matter, which is on solid cohesion. We started this about 5 days ago, so if you want to go to the start, you can go back about 5 episodes, but we're here in the middle of chapter 1. He just derived through a derivation that somewhat opaque, but he derived an expression, an equation for like a single force for now what does he call it? The rotational force for one particle that it exerts on another, and that is log of t. So he uses the natural log because it's an integration that you have to use because even though motion comes in discrete units, it is a continuous motion. It's something that I'm having trouble with myself, but moving on, we're going to start here, and hopefully we'll be able to get a little bit of a chunk going here today. So the force computed from equation 1-1, which is the log of t, where I'm trying to see where he because he was using n and then he switched over to t, and excuse me. To evaluate the rotational force, we integrate the quantity 1 over t from unity, the physical datum, or 0 level. Again, that's unity, unit speed, to t. And then the force computed from equation 1-1 is the inherent rotational force of the individual atom. That is the one-dimensional force which it exerts against a single unit of force. The force between two apparently interacting atoms is log of T(A) times log of Tb. And again, this is a force between two apparently or as if interacting atoms. As if he uses, or apparently, because say if you have the balloon example again, and you contract the balloon, and so all of the dots are moving toward each other, it appears as if there is a force field between each one of the spots, that they're moving toward each other. But that is only when you assign a reference point to one of them. When you say that one of them is motionless, then it appears as if each other dot is being moved toward that reference dot as a action at a distance, and there's a force field between them. But that's not what's really happening, because what's really happening is that all of the dots are moving toward all of the other dots, and the dot that is motionless is actually moving. And so it's an as-if force. The numbers work out the same way as if they were attracting in a force field, but they're not. But that you can still use the same math because that's how it appears. So so the force between the two apparently interacting atoms is log of Ta times log of Tb. For a two-dimensional magnitude, two-dimensional magnetic rotation, and again, the atom is comprised of rotations in a universe of motion. There are four kinds of motions, and the atom is made out of a three-number set. At Larson's periodic table, basically each atom is three numbers. The first is the primary magnetic rotations. Those are two-dimensional rotations. And then there is a secondary two-dimensional rotation. And then there is a one-dimensional rotation, which is kind of like a spin. And so for a two-dimensional magnetic rotation, this becomes log squared of Ta times log squared of Tb. As we found in Chapter 12, Volume 1, Nothing But Motion, the equivalent of distance s in the time region is s squared. And again, so that is the time region, which is because of the discrete unit postulate. And so the time, if you don't have a full unit of space, then you do not have space. You only have time. And so when you're dealing with, and 1 unit of space is 4.56 times 10 to the minus 8 meters. So if their interaction is occurring in less space than that, then you don't have space. You only have time, because the universe is made out of space and time only. And so it's got to be one or the other or both. And so if you don't have space, because you don't have a full unit, you have only time. Larson refers to this as the time region. And in the time region, you have kind of the directions invert. Gravitation becomes outward, and the progression becomes inward. And the units also change. So the equivalent distance in the time region is s squared. So if you have s in the outside region, the material sector, what he calls the time-space region, in the time region, that same distance is s squared. And the gravitational force in this region, therefore, varies inversely as the fourth power of the distance rather than the square, because gravitation is usually operating under an inverse square equation. But again, this is an as-if force, so it doesn't really exist, but you can still use the math. Applying this factor to the expression for the force of the two-dimensional rotation, together with the interregional ratio, which is basically the ratio of things that are not lost in the translation. When you're looking across into a different sector of the universe, like looking into the time region, what you see is only part of what's going on, and a very small part of what's going on. And so you have to use the interregional ratio, which is for an atom is 156.44, which Larson calculated in a video that in a paper that he wrote, in a video that I did months and months ago. So if you want to go back, and you can look for the video called the interatomic region, or the interregional ratio. Okay, so you have the fourth power of the distance, and you apply this factor to the expression for the force of the two-dimensional rotation, together with the interregional ratio. The ratio of effective to total force is how he phrases it. The ratio of effective to total force, derived in the same chapter, chapter 12 of volume 1, which is nothing but motion. We obtain the effective force of the magnetic rotation of the atom. So what you have is that fraction 156.44, 1 over that, which in decimals is 0.006392. And then you multiply that by the fourth power. And then you take S and you multiply that by the fourth power. And then you multiply that by log squared of T A and log squared of TB. So that is his equation for the force between two-dimensional rotations, two atoms. The distance factor does not apply to the force due to the progression of the natural reference system, as this force is omnipresent, and unlike the rotational force, is not altered as the objects to which it is applied change their relative positions. At the point of equilibrium, therefore, the rotational force is equal to the unit force of the progression. Okay, so the progression of the natural reference system, the motion outward at the speed of light in all directions, except now it's in the time region, so it's moving inward instead of outward. And the number we're looking for is the interatomic distance, and that is the place where the progression and gravitation reach equilibrium. And so what we're looking for here in this gravitational force equation is we're looking for the place where it equals the progression. So where those two quantities are equal would be the place where the equilibrium is established. So here he says, as this force, the force of the progression is omnipresent, 1 over 1 equals 1. This is the progression of the natural reference system, and it exists. He calls it the null point, or the neutral point, or the origin, the ether. The progression of the natural reference system. It is always there, and it's always the same. But gravitational force is variable. He calls it the rotational force here. And it's so the progression is not altered as the objects to which it is applied change their relative positions. At the point of equilibrium, therefore, the rotational force is equal to the unit force of the progression. Okay. Substituting unity for f of m, fm, in equation 1-4. So we're really saying that this force equals 1. We obtain 0.006392 times log square root log 1/2 T A times log 1/2 TB. I'm kind of lost here, but that's really just the algebra that is messing me up here. He substitutes S sub 0. So he's basically, it was originally log squared, now it's log to the 1/2, because he's dividing this by fourth power relation of the gravitational force. So that's what we end up with. S sub 0 equals 0.006392 times log of 1/2 TA times log to the 1/2 TB. The interatomic distances for those elements which have no electric rotation, the inert gas series, may be calculated directly from this equation. Okay, so this equation is only good for the noble gases, because the noble gases are the only elements that really have a 0 as their third number in Larson's classification. Now remember, I said that each element in Larson's universe of motion is a 3-number set. The first is the 2-dimensional primary rotation. The second is 2-dimensional secondary rotation. And the third is the 1-dimensional rotation. The 1-dimensional rotation is optional. And the 1-dimensional rotation can be positive or negative. But when the 1-dimensional rotation is 0, that basically is entailing that you're on the column that is the noble gases, the heliums and the neons and the argons and kryptons, xenon and radon. Okay, so those are the only elements that you can calculate with that equation. Now, if you're talking about an element that has an effective kind of C component, the 1-dimensional rotation, then you need something more, or maybe something less. But the interatomic distances for those elements which have no electric rotation, the inert gas series, or noble gases, may be calculated directly from this equation. In the elements, however, T sub A equals T sub B in most cases, and it will be convenient to express the equation in the simplified form. Thank God he's simplifying something, right? S sub 0 equals 0.006392 times log of T. Okay, that is because in most cases, the first number and the second number are the same. I would think that would only be for half of the elements, but he says most. T sub A equals T sub B. Okay, so that is the equation that you use for the inert gases. Okay, the values thus calculated are in the neighborhood of 10 to the minus 8 centimeters when you're using an equation like that. And he's basing everything on a unit of space. 1 unit of space is 4.56 times 10 to the minus 8 meters. Okay, so this is a fraction of that. This is, 1/100th of that. If T is at, a number in the single digits, which it is for all these different elements. Okay, so, and for convenience, this quantity has been taken as a unit in which to express the interatomic and intermolecular distances. When converted from natural units to the conventional unit, the angstrom, which is, I believe, 10 to the minus 9 meters, equation, that equation becomes S sub 0 equals 2.914 times log of T, A. So 2.914 angstroms is the standard value here for when TA equals TB, and 2.914 angstroms times the log of T. Okay. In applying this equation, we encounter another of the questions with respect to terminology that inevitably arise in a basically new treatment of any subject. The significance of the quantity T as used in the foregoing discussion and in the equations is obvious from the context. Did you think it was obvious? I didn't, but maybe that's because I'm just a historian. But okay, so the significance of the quantity T as used in the foregoing discussion and in the equations is obvious from the context. It is the magnitude of the effective rotation. But the question is, what shall we call it? The basic quantity with which we are dealing. I have to also add that whenever you hear Larson using the term obvious, it's never obvious. I think he uses that term as a cover, because I've seen him use it a number of different times and places, and I think he kind of wants to shame you into thinking that you're the dummy for not understanding where he's getting this from. I think he uses this kind of as a subterfuge for, okay, that derivation that I just came up with is a little bit tenuous. It's a little bit hard to follow. So I'm going to use the term obvious to make sure that people go back and look at it some more or something. So what shall we call it? The basic quantity with which we are dealing, the rotational speed displacement, does not enter into the equations directly. The mathematical structure of these equations requires us to enter them with values that include the initial unit, which constitutes the natural zero datum. Furthermore, each double vibrational unit rotates independently, and when the rotation extends to a second such unit, the increment in the value of T is only one half unit per added unit of displacement. Under these circumstances, where the relation of the term T to the displacement is variable, it seems advisable to give this term a distinctive name, and we will therefore call it the specific rotation. Okay, so that's what he calls it, the specific rotation. Now, I'm no less lost right now than I usually am when I read this chapter. I get it kind of in total, and I understand the equation, and I kind of understand how he derived it. Certainly not well enough to check its veracity or to verify it. But I can see that there is some kind of logical process there, so I'm just gonna give him the benefit of the doubt and say, well, if I really understood what I was doing, I could derive the same equation. And I will hopefully see you applying the same type of equation in a later context, in a different field, to show that this is consistency. But I just think that, he's kind of just hitting you with too much too fast here. And I don't blame him. Whenever I criticize Larson, I don't blame him, because I know he's one person doing just a Herculean task. He has to do the job of like 1,000 different scientists at once here. So he's really got a thankless and impossible job to do, and he's trying to do it the best he can, and he's doing it better than anybody else that I could really see. So I'm not really, criticizing him. I'm just coming from my own perspective of, okay, I'm having difficulty with this. And yeah, you could have, if you did this, I wouldn't have so much difficulty, perhaps. But I don't know, maybe I'm a hopeless cause. But I think we're going to stop right there. But I just think that if he just, turned this chapter into 5 chapters instead or something, and just walked you through it, and, from every angle, okay, this term means this, because he's throwing in all kinds of new terms here. Now, so what he's saying here is, each double vibrational unit rotates independently. Okay, these are, I believe, well, I don't, because a vibrational unit, I don't remember where the vibrational units are coming in. And then he says, when the rotation extends to a second such unit. Okay, the double vibrational unit, I believe, is the photon at the core of the atom. So we might have to go back and revisit this paragraph when we come back tomorrow. So I'll back up and do that, and maybe, because I think I'm at least understanding where he's coming from now. I mean, that's the only approach that I really have to do this Larson right now, is just to read the stuff over and over and over again and hit myself over the head with it until I get a clue. And usually then I can move on to the next paragraph or whatever. But here I got lost by the terminology, and I didn't see that word vibration. So, okay, we'll go back and we'll try to clarify that and move on. Don't lose faith. We're gonna get this. Thanks for tuning in today.